And I'm going to share screen. Okay. So hopefully you can see my screen. So today we'll have an introduction to the topic of the course, and I'll give an overview of the structure of the course and the evaluation of the course. So the course is called La Web de Datos, the web of data. And what does this mean, right? So we're going to talk a little bit about what the topic of the course is. So we have to start with the web. Okay, so we all know the web. We all use the web every day, probably. The web is now 3 decades old. Okay, so it started in 1989, invented by Tim Berners-Lee while he was working in CERN. So it's been with us for quite some time.
Okay.
Voilà, sí. Okay. So the web is now 3 decades old. So this begs the question: what would the future of the web look like? Right. So what will the web look like in 3 decades' time? So if we think about this, it's a pretty difficult question to answer, right? If you were to think we are now in 2020, so that would be 2051. What would the web look like in 2051? Okay, that's a tough question. So if we think about it, we might imagine something that we've seen maybe in a movie. We might imagine some sort of very fancy interface, something virtual reality or augmented reality or something like that. So it's possible that we might go in this direction, but these are more interfaces to the web, right? So we might also imagine that the web might be faster, it might be easier to connect in different places. It might be um, more widely available. But again, this is not really fundamental to the web. Okay, that's actually more related to the internet, for example. So in general, what I'd like to talk to you about is a proposal of how the web could evolve in the next 10, 20, 30 years, maybe even shorter, okay, which is called the semantic web. And it's a fundamentally different way of dealing with the content of the web, of representing the content of the web. So what is the semantic web, right? So if I have a question, what I will usually do is type my question into Google, and I'll see essentially what Google suggests. So if I search for the semantic web on Google, it'll return me various pages that describe, for example, this is based on one of the original definitions of the semantic web by Berners-Lee, the same person who proposed the web itself. So Berners-Lee proposes that the semantic web will bring structure to the meaningful content of web pages, creating an environment where software agents roaming from page to page can readily carry out sophisticated tasks for users. So, okay, that's kind of maybe a little bit difficult to understand. Okay, so what exactly, what is this idea? What does it mean? So it's not so easy to answer in simple terms. What is the semantic web? I will try today to answer that question more or less, or to explain the main concepts. But it's essentially as well also quite difficult to explain what is the web, right? So if you were to imagine explaining to someone who didn't know what was the web, or explaining to someone maybe in 1990 or 91 when the web was not well known, what is the web? It's not very straightforward. You could explain it in technical terms. You could explain about HTML. You could explain about HTTP. But that doesn't really capture the full idea, does it? Or the full impact or the full consequence of what the web means for people. Um, you could maybe explain about certain applications, like you could talk about Wikipedia, but then people would say, oh, well, I've got an encyclopedia in my house, so what's the difference? Why would I need that? Or you could talk about finding flights, and people would say, well, I have travel agents. Why would I need that, right? So it's not so easy to answer. But of course, it's something that we'll be answering over the course and in the class today. I'll give you the main concepts of what the semantic web is. So to ask what is the semantic web, it's a good idea to rather ask a different question. Why do we need a semantic web? What is the problem that the semantic web aims to resolve? So what is the goal of the semantic web? So the current web is great. I'm not going to bash the web. It's one of my favorite web pages, sometimes red, sometimes blue.com. So we all know that the web is amazing. So why do we want to change it, right? So just because it's so useful, it doesn't necessarily mean that it's actually perfect, right? So if we want to find information on the web today, Google is pretty great. So for example, if I type in my search movie What's in the Box, anybody got any idea of what the movie would be? Yeah, so there's some people in the chat got it. So 7. And of course, Google knows exactly what we're talking about, right? So it will return 7. So we also have Da-Da-Da-Dum Symphony, which, okay, if you've taken a course with me before, you know what this one is. Some of these slides you might have seen before. Da-Da-Da-Dum Symphony would be Beethoven's 5th. Google knows what you're looking for, and Google can even tell you what you're searching for. You can also predict what you're looking for. So Google works very well. Not complaining about Google at all, but it's still not perfect for finding information on the web. I'll explain one major part where Google does not work well, one major scenario. Okay. So any questions or doubts this far? Okay, so let me explain a concrete problem with the web. So it's an example where a user of the web is doing a report for university, and she wants to find all Nobel Prize winners in literature who fought in at least one war, the year they won the prize, and the year the war started. Okay. So how would you find this information? How would you go about finding the Nobel Prize winners in literature who fought in at least one war, the year they won the prize and the year the war started? So this is a pretty tough question, right? You could try Googling it. You could try, Nobel Prize winners in literature who fought in a war, but you're probably not going to have too much luck if you search for it, unlike the other cases we saw. So how do we solve this? Probably on the current web, what we'd have to do is find a list of, use Wikipedia, essentially lots of Wikipedia tabs. So we would have to maybe start with a list of Nobel laureates in literature. Then we would have to go through the list, click on each one, and then within that document, we would have to search for some words like war, conflict, civil war, battle, and so forth. Navy, army, all these sorts of keywords to try to find somewhere in the document that speaks about some war he might have participated in. If we find it, then we have to visit that page. We have to extract and maybe copy and paste the dates into a spreadsheet. Then we need to return to make sure there's no other wars. We need to go to the next winner. We need to to do a similar process, and we need to iterate over all the winners, all 100 and whatever, how many there's, 120, 130 winners. So this is obviously going to be quite a frustrating task. Okay, so we see that this is not so easy, right? Google can't really help us here. So how does this work more formally? Well, we take all the Nobel Prize winners in literature. We take the year that they won the prize. We have to search for all these different keywords in the document. This is just some examples, not a full list. Then for all the wars that we find, we have to go to that page and we need to get the starting year of the war. and then we need to somehow add all this data to the results. Okay, so this is a lot of manual work, right? Especially if we have, at least here, we have some sort of bounded list that we can possibly feasibly go through. Right? So we could feasibly do this, right? But it's easy, it's not difficult to find other examples of questions where this would be infeasible because the number of elements here is just too much for humans to handle. So maybe 6 decades on from now, maybe what we could use is the semantic web. We use our function magical semantic web results. We get our results and we automatically, the web will return them for us and we return those results. So this would be nice, okay? Be a lot more simple, wouldn't take as much time, and probably it would be a lot more accurate because we're not going to miss some keywords in the document or what have you. So since the machines will be doing it, the machines are very efficient and precise, we should expect, assuming the data themselves are precise, we should be able to get very good results. So of course, how does this magical semantic web results function work? That's something we'll have to explain during the course. That's essentially the topic of the course. Okay, so an interesting question is why doesn't Google help us here? Why is this query hard on the current web? So what's so difficult about this query? Any ideas? Algunas ideas pueden responder en español también, no hay problema. So why can't Google find the results? Yeah, so one response is that the data are unstructured. So essentially, if you thought about the data being loaded into a database and you knew a bit of SQL, somehow imagine like all the content of the web was structured as a database and you could somehow understand the schema of the database and you knew SQL, right? Then you could somehow think about answering this sort of question. So you could think about writing an SQL query to find this if the content of the web were structured. Put another way, Google is very good. The Google web search is very good at finding documents. So if you put in some keywords, it's very good at matching those keywords and finding documents that contain those keywords. However, if you if the answers you're looking for are not contained in one document, but rather spread out, the information is spread out amongst lots and lots of different documents, Google doesn't help you. Google will just return you a web page, right? So fundamentally, if there doesn't exist a web page with precisely the answers you seek, then Google can't help you. And of course, there exists web pages with the answers to an almost unbounded number of questions on the web because people want traffic and they're going to answer the most common questions that people would have, and that will bring them traffic from Google. But there are always specific questions that will not be answered directly by any one web page. So this is one example, which is kind of specific. It's a report for university. So how many times, you could ask, how many times do we want to answer these sorts of questions? And I think my claim would be that we want to answer them all the time. So maybe we think Google is great because we subconsciously we wouldn't Google for this because we understand that it won't be able to help us. There are other cases where we have specific needs that aren't responded by a single web page. They could be contextual. Another example I use is finding recipes with the ingredients available in a local supermarket. So this sort of query depends on where I am right now, what sorts of recipes I'm interested in, what the current stock of the supermarket is, whether the supermarket is open or not. So my claim is that we actually could use the web to answer all sorts of queries, all sorts of questions that Google is not helping us with. Why? Because the question is so specific that it's not worth anybody's time, or nobody has created a web page dedicated to that, or the web page would need to change all the time, or the question is completely contextual, this sort of idea. Yeah, okay. So it's hard on the current web because there doesn't exist a single web page that just gives us the answer. Okay. So what's the problem? Why is it a problem that the data are on one single web page? Essentially, the problem is that once the answers are spread over multiple web pages, it's up to humans, to users, to manually integrate and solve the task they want. So why is that? How does that come about? Well, the current web is document centric. It was always conceived of as a document centric thing for publishing hyperlinked documents. There was an earlier version of the web that wasn't based on this, that was proposed, but also by Berners-Lee. But the web that won, let's say the web that everyone or many people use almost every day, is document centric. So let's have a look at a document. So the format that we use on the web is HTML. Okay, so we can define a document by nesting these XML-like, SGML-like tags, which describes formatting instructions and content for a document. Okay, so we define a paragraph, we define another paragraph, and this is maybe an interesting part because we have a link to another document which goes here, and this document similarly is described using HTML, for example. Okay, so this is the basis of the web. So quite simple and hugely effective. So most of this web content makes sense to humans in the sense that humans can these documents and they can understand, okay, we're talking about a country, there's a city there that has 1 million people, the city is called Dublin, maybe the human understands some background knowledge, has some background context for all of this that helps make sense of the documents. For example, she might know that people in Dublin drink lots of Guinness. So it's not represented in the documents, but it's somehow background information that can help to contextualize or make sense of these documents. Of course, this assumes that they speak the language, right? So maybe the user doesn't speak Spanish. I think she does later in the slide, so a little bit inconsistent, but anyways, let's assume for now she doesn't. So, okay, she can read this document here, but won't understand the population of the country, for example. And generalizing this issue, essentially it's much worse for machines. So if we think of a machine looking at the current web, they don't understand natural language really very well. So how does the web look like to them? Essentially, all I've done here is I've jumbled all the letters. So it's like an alphabet cipher. So I've just mapped letters one to one. And what's the purpose? The purpose is to sort of give this idea of what the machine can understand. So what the machine can see is that, okay, there's there's a title with 7 letters followed by an image, and there's 2 paragraphs, and there's a link. But in terms of the actual content of the web pages, it's something, this is what they see, right? They see that there's an image that has this size, there's a title, there's a paragraph. They can sort of understand these because they've been hard-coded to display HTML documents. But the actual content of the documents is as hard to understand as this document, even harder because we could decrypt the cipher, but even it's hard for them to understand what's going on, right? So this is what the web looks like to a machine. So they don't really understand the content is opaque. They cannot really access the meaning or the semantics of the content. So what's the problem? Why is that a problem? So what machines on the web are asked to do, what we're asking the machines to do essentially is to fetch documents on the web. Machines talk to other machines, they fetch documents using HTTP protocol, and they return a HTML document to the user. Okay, so they're basically messengers and storage systems that they can pass between each other, these documents that people are looking for. But they never really understand oftentimes they don't understand the content of the documents. Another task they can do, okay, well, we can have a special machine that indexes the web, which is like Google and other search engines. So the user makes a search, and then this machine or several thousand machines collaborating in a distributed system can go off on the web or on an index of the web that they already have. They can try to do some string matching, essentially keyword matching. Okay, maybe a little bit more intelligently, like they can lemmatize words, normalize words, and so forth. They can find documents and they can return those documents. And they do this very, very well. Yeah, so and there's lots of cool tricks they can do. But it's still, essentially, the documents are not really understanding neither the query itself nor the document. Okay, so this is starting to change a little bit, but essentially the machines are just somehow doing some dumb pattern matching of letters and words to documents. So what machines cannot do is intelligently combine sources. So they cannot, for example, take two documents, read them, and then give an answer that's based on the content of both. Right? So they cannot do this because they don't understand the documents. They can't intelligently combine the content. So the idea of a semantic web is the idea of a web where machines can understand the web. Okay, and I put understand in quotes, right? So, okay, essentially, okay, in the same way that the user understands the web, we would also like somehow machines to be able to emulate a sort of human-like understanding of the web. So in the same way that humans can sort of read something and infer new knowledge, they can combine data from multiple places, they can somehow gain new knowledge or understand new things by reading the web. Of course, they have to be careful. You can't trust everything you read on the web. But machines, likewise, what we would like is that machines could somehow understand that. And if machines could understand the content of the web, then they could process it at a much larger scale and much more efficiently than humans, which effectively would mean that we could automate a lot more tasks on the web. So we could automate many, many more tasks. So, okay, what do I mean by understand? Okay, so what do I mean by understand here? What do I mean machines that understand? How can a machine understand anything? So often I'll use words like this, but I quite like this quote by Dijkstra, which is the question of whether computers can think is like the question of whether submarines can swim. So I know in a more general audience, if you started talking about machines thinking and understanding, people might get misled by what that means. But I think you'll understand what I mean if I say understand or think. I mean emulate a human-like understanding of the content, right? I don't really mean that they're understanding the content in the same way as humans, but somehow that's what we're trying to emulate. So I don't want to get into too much philosophical questions about thinking and understanding. But okay, getting into more philosophical questions. There is this thought experiment. Let me see how we're doing for time. Yeah, we can maybe do this part. So there is a thought experiment which is called Searle's Chinese Room. So how this works, it's a thought experiment where we have a room which is somehow self-contained, or let's say blocked from the outside world. And there is inside this, inside the room, there is an operator, and the operator does not speak Chinese, does not speak Mandarin or Cantonese, and doesn't understand Chinese symbols. Okay, so the operator has a rule book. Okay, and this rule book is very large, as we can see. It offers lots and lots of details. So on the outside, we have two people who speak Chinese or Cantonese Mandarin, and they're passing messages through this room. So they don't know anything about the contents of the room. So they pass in a message. Then the operator in the middle takes the message, somehow uses the book to figure out what the output should be, and then returns an output. Okay, so the main idea is that the operator is responding to inputs and returning outputs in a language that the operator does not understand, using a rule book. Okay, and then the question is somehow, is this Searle's question, which is maybe not so important for the class, but Searle's question is this operator here understanding? Is this box, this system somehow can we say that this system is processing, is understanding, is thinking, is somehow in terms of Chinese symbols, is this sufficient for understanding? Which I think this is sort of a question of what the word meaning and intelligence and all this sort of means, which is maybe not so interesting. But what is interesting is that this is what we could think about with the semantic web, that we have users on both sides that have their sort of human-like semantics, and we have the machines in the middle who are just using a rule book. They're kind of cheating, but they're going to be responding somehow in a way that's convincing to speakers of a natural language. To be able to take queries or take tasks and to be able to respond to them in an intelligible way. So, okay, so we have the machine here. This is essentially this idea that we can maybe start to build a machine that can emulate this sort of behavior. So how does this work? Essentially, well, we still have a major problem, right? So what we have here is the sort of human world. Okay, so I've encoded it again, so it's not obvious. So we see the challenge for a machine. And we have these two documents, and what we have is a question from the user. So this is the machine, and the machine somehow needs to respond to this question. So how do we build a machine that could do that? Okay, so we might think, deep learning. We could use, some deep learning models. We could train it on lots and lots of different data, lots and lots of different questions. But what happens if we've never seen this sort of question before? What happens if, essentially this is still not something that would be solved in deep learning. There's some very good systems for finding answers explicitly in text. But what happens if the question involves information spread across multiple web pages? There's still no techniques to address this, let alone like get a 100% precision or very accurately if this were an important task. So what should the output be? Any ideas? Okay, so the output should obviously be Uli Mosul.
Obviously.
Not so easy to figure out, right? So if we look at the question, what does it mean? And we'll see it later. I think, do I have it in the question? I think it is, what is the population of the capital of Ireland? And this will be 1 million, I think. Spoilers, I'm not sure if we see it later. Okay, so why is it so difficult for machines? So if we look at the problems, let me see actually what time it is. Okay, we can take a break actually for 10 minutes. So we can come back at 10:55. So the other thing I have is there's a calendar for Pausas Activas, so I'll post the link in the chat if you want to participate in that. Let me see. Stop sharing. So let's return to the class. So rather than asking the machines to understand unstructured natural language, what if we could structure everything? So, oh, I jumped ahead, I'm sorry. Oh. Yep. Okay. So why is it difficult for machines to understand natural language? There's multiple reasons. So first problem, we have multiple names for one thing. So we could talk about Ireland, i.e. Irlanda, Republic of Ireland, and so forth. So we understand that these are all maybe talking about the same country, more or less. But the machine might see 4 different names and might think, oh, these are 4 different things. We might also have one name for multiple things. So we might have Dublin, which refers to a city in Ireland, a city in Ohio, US. as well as an Irish bar in Bella Vista. And the machine will probably think this is one thing, right? Not really know what it is, but since it's the same name, might assume that this is referring to the same thing. We might have multiple ways to say the same thing. So we could say Dublin's population is 1 million, Dublin has population 1 million, Dublin's population is 1 million in number, and Dublin has 1 million inhabitants, 1 million people live in Dublin, its population is 1 million. So mentioning Dublin in the previous paragraph, or we could say it in a different language, la población de Dublín es 1 million. So, okay, the machine is having a lot of difficulty at this stage understanding what's going on. We might have multiple meanings for the same sayings. Sherlock saw the man using binoculars. So what does this sentence mean? Actually, it's ambiguous even for humans, right? So it's possible that Sherlock saw the man using binoculars to see the man. Or it's possible that Sherlock saw a man and that man was using binoculars. Okay, so the machine is definitely frustrated at this point. Also not saying what is meant, which is very common on the web. Fred está arriba la pelota. Fred is on the ball. Means something different in English, actually, the idiom. So the machine in this case thinks, oh, okay, I understand this one. This one makes sense to me. But that's not the case. Okay, so it's not literally that he's on the ball. So the machine is obviously going to struggle to understand the content of the web with the natural language and so forth. So how can we address this semantic gap, right? So this gap in meaning between the two worlds. We're probably never going to address it entirely, of course, because machines don't experience the world the same way as humans do. But at least for factual content, we can start to address this gap in a meaningful way by structuring everything. Okay, so rather than asking machines to understand that the natural language of humans and the context of humans on the web, we could structure the content of the web, publish content on the web in a format more friendly for machines to process and to be able to run tasks over. So rather than having, for example, multiple symbols for one meaning, what we could do is somehow just have one symbol for one meaning. This is just some symbol. It doesn't really have any meaning, but we're going to assign it to the country. One symbol, one meaning also means that we can't have one symbol referring to multiple things, right? We just have one symbol, one thing, okay? One simple way to say one thing. We're not really interested for machines in the prose, in the way that the facts are expressed. We're just interested in the facts. So we could think about structuring very simple claims or sentences. Dublin population 1 million with 3 elements. And this is something more recognizable to a machine. Okay, so we don't really define a symbol for the numbers because the numbers have some meaning for a machine. It can add numbers, divide numbers, subtract numbers, okay? So we just have one simple way to say one thing using the symbols that refer to those elements. Okay, so, okay, we saw that this was, pretty much impossible to answer from our perspective, looking through the machine lens of the web. So what about in this case? If we structure the web, now we have these simple combinations of symbols that represent claims, okay? The machine still has no clue what these symbols refer to, right? But now given a question that's similarly structured, where we have these variables that we want to replace with something, what would the output be? What would we match to X and Y in this case? So this is interpreted as an and, as a conjunction. So what would fit here, this question? So if we look, we have no idea what these symbols mean. We look through and we say, okay, we're looking for this sort of H-like symbol. If people are into astrology, interested in astrology, these symbols will make sense. They don't refer to anything in particular here. They're just random symbols. But if we look through and we say, okay, in this case here, we see somehow this symbol matches this symbol here. We see that this here matches here and here. So we would say, okay, probably this symbol would match X, okay? And if that symbol matches X, then now we're looking for a triple simple claim that starts with this symbol. And we see there's one here, and it matches this element here, and then so we would expect Y to be 1 million. So without being, and one could imagine writing an algorithm, some code to do this, right? Automatically, it doesn't require a deep understanding. So without really understanding the content at all, we can respond to this. We can somehow respond to this question because it's structured, and we can return a response. So what does this look like from the human perspective? So what this looks like from the human perspective is this, okay? So from the human perspective, it's Ireland capital X, X population Y. And we see how the facts are represented here, okay? So from this perspective, we can understand what the question means, and we can understand somehow what the output refers to. So somehow this is somewhere between both worlds. It's something humans and machines can work with and understand. So this is the idea of a symbolic approach. Somehow we identify symbols that are opaque to the machine. The machine doesn't know what they mean, but the machine can process the symbols to generate results. Okay, so here we have a simpler question. That's actually a more complex example, but we have this question, which is X sun, I think, X symbol Y. And we're looking for somehow the output of this question. So this one's relatively straightforward. We see that the symbol only appears in one place. So we would expect X to go to the sort of H thing. I don't remember what this is probably Aries. So we match X to this H thing, and we match Y to, I guess, Aries. And we get this response here. Okay, so this is pretty straightforward. But if we look at what the question was in the human language, what we're asking is X is part of Y. We're looking for things that are parts of other things. So we get Ireland as part of Europe, but would we expect more answers here? Is that the only answer we would expect as humans if we look at these claims here? Is there any other answer we might expect? So somehow using some understanding of what the part of term means, we would also expect, for example, to know that Dublin is part of Ireland, right? So if we have something like A is capital A, capital B, then we would expect to have something like B part of A, right? So it's not just literally symbol matching, but we also need to maybe understand some of the semantics of those symbols to be able to generate good answers. So we would expect an answer like Dublin, X matches Dublin and Y matches Ireland. So how can we enable this? Well, we can define some rules. So we can define some rules, for example, to say, if we have B, some symbol here, this symbol A, then we want to imply A sun B, okay? So in this case, if we match this part of the rule here, we see that it matches this claim here. And then we should imply A sun B, which would be invert the symbols, and then we replace the predicate here, the part in the middle. So what should the output be now? If we apply this rule over the data to extend the data somehow, and then we ask the question again, we can get some additional answers, right? So we can get this new answer here, which is based on the rule, right? Which it comes from this triple here, which we've flipped around and we've changed the symbol in the middle. So what are we looking at from a human perspective? What we're looking at essentially is the rule that B capital A implies A part of B, right? So we apply this rule, and it allows us to generate some additional answers to our question, symbolic question. So we're still missing one, right? We're still missing perhaps the rule that Dublin should be part of Europe. So because if Dublin is part of Ireland and Ireland is part of Europe, then Dublin should be part of Europe. So how should we deal with this scenario? We need another rule, right? So what we need for a rule here is for the transitivity of part of. So what does transitivity mean? It means if A has some relation to B and B has the same relation to C, then A has that relation to C. Okay. So for example, ancestor of would be another good example. If A is ancestor of B and B is ancestor of C, then A is ancestor of C. In this case, A part of B, B part of C, then intuitively A part of C. So what should the output be? We apply these rules recursively until we don't find any new data, any new symbolic claims. And we run the question over it again, and the output we'll get this time will have 3 answers, 3 different pairs for X and Y. So as humans, what we would see is these claims here, and we would see these results here. So Dublin, it matches Europe. Okay. So we start to see how we have some idea now of how we can have machines work with the content of the web to be able to combine and generate new interesting answers for questions. So this is not exactly like the natural language questions we saw before, but it's a simplified form of natural language, let's say, and something that the machines can process, and also something that we can more or less understand, maybe with some effort. And the machines with some effort can also process. So somehow we're meeting the machines in the middle. Excuse me. So overall, this is sort of the core of the semantic web idea, you know, on a technical level, in a technical sense. We have structured data, okay, which will be based on a very simple data model, which will be based on these sorts of triples, this subject, predicate, object claims. Subject, first element, predicate, the middle, and the object, the third element. So we have these triples, and we have these triples published on the web. And then we have some sort of logic layer, which is maybe rules or something called ontologies, which I'll speak about later. That defines some of the semantics of some of these symbols. We have the semantics in terms of if you have these data entail or imply these other data. We have queries, again, in a structured format that's very similar to the structure of the data, so that machines can do this sort of symbolic matching. And then we have our output for the humans to consume. So this is more or less the kind of concept of the semantic web. Any questions or comments? Okay. So where is the semantic web, right? So the semantic web idea is not so new. The semantic web has been around, or the idea of the semantic web has been around for over 20 years. So maybe many of you haven't really heard of or seen the semantic web before. It's not something that's talked about all that much, I would say. So, you know, what's happened in the last 20 years? Why has it not taken off? Why are we not using the semantic web when we load up our browsers? Why doesn't it say welcome to the semantic web, right? Okay, so essentially the semantic web is not really like that. So the semantic web is not intended to replace the web, the current web, or anything like that. It's not that we're going to upgrade to a semantic web. The idea is that the semantic web is somehow forms part of the web itself. It's somehow an upgrade to the infrastructure, the technology that the web uses, with the new standards and languages and techniques to be able to deal with the data on the web, structured data on the web. So in general, all of you have seen or are using implicitly parts of the semantic web when you use the web. You might not have realized it. So I'll give some concrete examples of projects, success stories for the semantic web, projects that I like, projects that have been successful, not a full list by any means, but some prominent examples. So the first is Wikidata, which if you've taken Base de Datos with me, we've already spoken a bit about Wikidata. It's a Wikipedia for data. So what is Wikidata? So it's a structured version of Wikipedia, we could imagine. So where you edit structured claims about entities rather than natural language documents. More interesting question again is, why is Wikidata? Yeah, so why do we need a Wikidata? Why is this important? So if we think about Wikipedia, which is sort of like an older sibling of Wikidata, right? So on Wikipedia, we have lots of different information about lots of different entities. And each of these articles about these entities is edited manually by human users. Yep. So users go in, they edit some facts, they edit some text. And in general, this has been hugely successful in the sense that lots of people contribute lots of time to improve and to extend Wikipedia. And it's a very rich resource. So if we look as well in the articles, we'll find these info boxes, which are these sorts of boxes of data, semi-structured data on the right-hand side of the articles. In this case, we have info boxes about Alexis Sanchez. So we see that we have information in different languages. So in this case, we have English, Spanish, and we have German. So if we look very carefully at these info boxes, we'll see a problem. Yeah? So we'll see that some of the information is not precisely up to date. So we'll see, okay, we're missing, these are snippets, right? So I've cut out parts of the information. So of course the Spanish version also has the date of birth and the place of birth and so forth. But if we look at information about the number of goals scored, we see that here it mentions that he has scored 82 goals for Chile. Here in the Spanish version, 82 goals for Chile in, I guess, 26 appearances. No, that couldn't be. No, this would be the other way around. So appearances, 82, 26 goals. Here it has 26 goals, 82 appearances, and this would be 25 goals, 76 appearances. So we see that these info boxes were taken at the same time. Okay, the data are maybe now out of date, but these were all taken at the same time, and we would expect the same data to be present in the different languages, because obviously the number of goals scored doesn't change per the language. So why do we have this inconsistency? We have this inconsistency because Wikidata requires users to manually edit the articles. So even though somehow this statistic here has nothing to do with the language, essentially a human user would still have to go in and update that data. And if the, Alexis is not so popular in German-speaking countries, then we can maybe expect that data to maybe get out of date. Okay, and this is obviously this is a bigger problem for Wikipedias or languages that are not well represented by Wikipedia editors. So we can have out-of-date information. Also, we have this issue of these complex lists that are somehow generated by people, right? So we have, if we think about Alexis Sanchez's goals, that information, that data are replicated not just across languages, but even within a language, it might be mentioned, or somehow there might be several articles dependent on that information. For example, to have a list in the Chilean national football team of the top scorers, to have the top scorers of a tournament, and so forth. So somehow there's a lot of replication of data in Wikipedia, which is done manually by users, and it's done for the convenience of the readers, so that they have these nice tables and so forth that they can read. They don't need to put all this data together themselves. It's there and ready for you to search in Google. So the problem is that when Alexis scores a goal, this creates a major problem for the human editors to be able to address. So now we need somehow an army of human editors to manually update lots and lots of different articles in different languages and different lists and so forth. So that's a problem. Okay, so this seems a bit antiquated, this way of asking people to manually edit and update data, right? So a way to address this, a solution or a proposed solution, something that's already working, let's say, is Wikidata, where instead of editing data in different languages, there's one central location where the data are edited in a sort of more symbolic, structured way. And then the different symbols are just assigned the labels in the different languages, right? So once we have a symbol, we can assign it the labels, and then we can use that symbol in multiple different facts like we saw previously. So this means that the data are structured, which is great for machines. You can do queries over them, structured queries. You can do lots of different types of processing on Wikidata. So this is something very much in the lines of the semantic web, and it uses the semantic web standards. So as some examples, we have, for example, Alexis Sanchez here. We have some data about Alexis Sanchez. We see very simple claims, sort of very similar to the symbolic method. So we have the first element here, subject, predicate, object, subject, predicate, object, subject, predicate, object. So we have this sort of triple-based representation of the data. And we see just a little snippet of some information. There's quite a lot of claims about Alexis Sanchez. So this is in English. We can then just translate the symbols to Spanish, to German. We see the same data underneath. We're just swapping the labels that we use for the symbols. Russian, and this language here. I don't remember what this language was, and it's very hard to find out to Google. Maybe somebody knows. They can put it in the chat if so. But I guess it's some Southeast Asian alphabet. I'm not sure. So if we're a speaker of this language, we can somehow get the data in a friendly form. Now, in this case here, we see that it shows the names. It doesn't show the names in the alphabet of this language. So in some cases where we don't have a good translation, it will just show the labels in a default language, in this case in English, okay, with the hope that somebody can go along there and edit that. So in general, we can go in here, people can go in, they can edit these documents, they can add more claims, they can change values, they can add references for claims. So the idea is that it's very similar to Wikipedia. It's a collaboratively edited, sort of structured knowledge base of the world's data. And that has similar ideas of notability, of inclusion and exclusion. So it's not that they will store all data in the world, but they have some notability requirements. So what does Wikidata describe? It describes 71 million entities. It has almost 23.5 thousand active users in the last 30 days that have somehow logged on or edited or done something. It describes mostly people, then species, places, buildings, events, chemical compounds, movies, streets or roads, astronomical bodies, stars, planets. It describes list articles, disambiguation pages. So this is mainly because every article in Wikipedia has a corresponding Wikidata entity. Wiki news article, scholarly article, this would be papers. Other types, or they don't have a type. So actually I'm just realizing this isn't ordered by frequency at all. So the most frequent actually mostly describes scholarly articles here. So lots of different information about lots of different types of entities. So what are the use cases? The first is to automatically generate these info boxes to resolve this Alexis scores a goal problem. So if we look at different info boxes, these things on the right of the articles in Wikipedia, and we pay more attention now, we'll often see that there's this little pencil. And if we look at it, it will invite us to edit rather on Wikidata. So we're not going to edit in the info box of one particular language, but we're going to edit the data in Wikidata, okay, which will then be somehow transformed into the info box of this language. So this is partially implemented. It's not true for all info boxes, only for certain info boxes that have the translation defined in a nice way. But our main use case would be for this info boxes, and this is going to be deployed more and more with time. So this again is populated. This is based on a one-to-one mapping. If we edit this here, then it's reflected here. If we edit this here, it will be reflected here. Okay. Another interesting use case for Wikidata is something that we can really hope to apply, or at least so conveniently and so for Wikipedia is to apply quality checks. In this case, what we're looking for are people who do not have an age between 0 and 130. So we get here a list of some very old people. So we're taking the difference between their, we're taking their death minus their birth to derive their age. So we see that there are some suspiciously old people here that might suggest that perhaps there's some issue with either their birth or their death date that needs to be revised. So you might say, okay, well, there are, you know, people who can live for a long age, and there have also been, you know, historical figures and legends that have purportedly lived for a very long time. So maybe there is not such an issue with having such a big age. These could be, you know, valid cases, but it's probably more difficult to explain the people who have a negative age. Okay, so the people who died before they were born. So these are probably definitely cases that need to be revised. So we can use Wikidata to generate queries that can generate these sorts of quality checks. And of course, it's important to know that Wikidata is, you know, like Wikipedia, it's fallible. It's not going to be correct all of the time, nor is it going to be fully complete. But the main thing is that people can edit and improve the data over time. So one of the cool things then is that we have this query service where we can go and we can get we can answer the question that we saw earlier. So let me see if I can quickly switch to share. Yep, share my browser. So we have here a query I made earlier. I wasn't going to type it in the class. What is this query looking for? It's the query that we saw in the class. So this is the query for all the Nobel Prize winners in literature that have won a war. Or sorry, that have all the Nobel Prize winners in literature that have fought in a war, the year of the award and the year that the war started. So we see we can run a query, and over Wikidata, since we have all the information about Nobel Prize winners and awards and so forth, we get a list of solutions. So it's possible, of course, that maybe we're missing some data, so therefore maybe we're missing some answers. It's also possible that there might be mistakes in the data, but as the data improves over time, this would become more and more complete, more and more accurate, this list. So we see that, okay, there's this problem of having to write this structured query here. Maybe, hopefully that wouldn't be so difficult for us by the end of the course, but for many users, this would be quite difficult. And there's an open question of how to make this sort of more usable. But we see that still, if we speak Sparkle, if we can manage to write our query as Sparkle, it's a lot less effort to get the data this way. So we can answer complex questions that integrate data from different sources using Wikidata. To take some maybe other examples, you can have a look here at this site. It's query.wikidata.org. They also have some visualizations, for example, where we can see some visual data. Okay. Oh, just realized, wow, we're nearly out of time. Time passes quickly. Okay, so I'm gonna just leave that to render. I think the answers were there, but it was rendering in my browser. So what I will do is I'll just give an overview of the course, because probably you might have some questions. I can finish the other part in the introduction on Wednesday. So to give since we're out of time, to give a brief overview of the course, the topics we'll cover, we'll talk about different semantic web standards and techniques, one for representing data, two standards for representing ontologies, which serve a similar purpose as the rules we spoke about, a query language, which we just saw in the example, linked data, this idea of how to link content on the web. Links are very important on the web. RDB to RDF, which talks about how to import data into the semantic web from relational databases, and shapes, which relates to the validation of RDF data. So it's a research course, which means that essentially there's not all the answers are clear. Not all the implementations are very mature. There's lots of prototypes, lots of open questions. In general, it's quite a different research area to many other research areas. Like, for example, in relational databases, that's something that's been around for a very long time. It's known what the issues and the problems are. And a lot of the research is in improving the technology that already exists, right? In this case, the research is more towards this vision of a semantic web that people want to realize. So it's a little bit conceptually different in terms of other research areas. So this might be one of your first research courses. So this is important to keep in mind, that somehow everything is more open, things are more uncertain, there's more proposals, more prototypes, so forth. So which makes it interesting, but maybe a bit different from other courses. Structure of the course, we'll have classes on Monday. We're similar to what we had today, where we'll see concepts. Lab on Wednesday, where we'll see the concepts in practice. And we'll have an auxiliary session on Friday for questions and answers, and also to work on the labs, to deal with projects and so forth. The marking structure will be, I'm not going to have any controls, or there will be no exam for the semester. There will be 75% based on the labs, the weekly labs that will be on Wednesday. There will be 20% for a project, and there will be 5% for a reading group, which will be where you will be assigned in a group of 3 to read a paper and give a short presentation about that paper. This reflecting the research aspect of the course. So hopefully we can sort of share some interesting research papers within the course. Bibliography, I'll upload a PDF of a book, The Web of Data. So, yep. But in general, you shouldn't need to read the book. It's more a reference. The content of the slides should be sufficient for the course. Outcomes, you can learn about the semantic web, which is, there's quite a few professors in the DCC who are interested in the semantic web as a research topic. Applied database and logic, artificial intelligence, etc. to the web. We'll see a mix of kind of theoretical and practical exercises. So we'll, in parts of the course, we'll get into more theoretical topics. I'll try to present it in an accessible way, but the labs will focus mainly on practical exercises. But I'd like to get into maybe some more theoretical topics briefly in part of the course. And maybe have some idea of in what direction, a better idea of in what direction the web might evolve in the next maybe 3 decades or even sooner. Right? It's already evolving in that direction. Any questions or comments? Okay, so I didn't fully get to motivate the semantic web, but we can finish the rest of the class on Wednesday. So on Wednesday we'll have the labs. The labs will be held in Discord. I'll post some information in the forum about that later. It'll be similar to what I did last semester if you took a course with me. So we'll just have a quite informal lab on Wednesday to motivate the course. And also to practice with Discord and get accustomed to all of that. Any questions about the class or the content of the course? Or pueden...
¿Una pregunta?
¿Sí?
Si subirá las cátedras, ¿y cuándo las subirá, antes o después de las clases?
I could upload them before the slides, before the class if you want. It's maybe a little bit easier to upload them after because I usually notice some mistake or something, I can correct it and upload it. But I'll upload them directly after the class. If you would like them before, I can upload a draft before. I'll upload them to a homepage that I'll link in the course. Generally, I'll upload them immediately. If I forget, you can let me know in the forum. The videos as well, I'll try to upload as soon as possible after the class. So I'll generally upload them to YouTube and to the homepage that I will link to from Ucursus.
Gracias.
Profe, ¿los laboratorios van a ser en grupos o individuales?
Yep. So the groups to work in the labs as a group, they'll be in groups, but you'll have to attend the lab session. You'll have to come to the Discord session to work as a group, and we'll take a list of the group members there, and only those people can work in the group. So if you don't come to the lab session, there's no problem, but you have to work alone for that lab. So if you come to a lab session, then that's okay. You can work as a group. So groups of up to 3 people.
Ya, gracias.
More questions? Time flies very quickly. Sorry for going over time. I'm gonna have to get a big clock in front of me or something. So we will chat on Wednesday. If there's no other questions, any other questions, you can ask in the forum if anything else crops up. So main thing for the moment would be to have Discord installed, but I'll post something in the forum about that as well. Okay, so see you on Wednesday.
Gracias, profesor. Hasta luego.